Welcome to E-Pathshala Architecture lecture series for PG students. And now I am going to talk in the module of solar water heating systems. And so these are the objectives of this talk. Initially, I will be talking on basics of solar radiation and solar water heating system and components of solar water heating systems and various types of collectors and solar water heating systems. And so initially I briefly tell about the solar radiation, and we have to understand about the sun and the sun's characteristics and the specification of the sun. And as we all know, the sun is a very big planet, and so from the sun we get all kind of energy resources. From the sun we get wind energy and biomass energy and ocean energy, and in ocean we have tidal energy and wave energy and ocean thermal energy conversion, etc. And from solar heat, and we have solar heat applications, and through solar radiation, and we have a solar PV system, and through which we generate electricity. And the energy generation is enormous from solar. And when we look at the sun, it is so amazing. The size of the mass is about 1.9 into 10 to the power of 30 kg. And if you look at the radius of the sun, it is about 6.96 into 10 to the power of 8 meters. And average density of the sun, it is about 1.4 and gram per centimeter cube. Average surface temperature, it is about 5762 degree Kelvin. And when we look at the solar mass, it is combination of hydrogen, which is about 70%, and helium 27%, and other matters 3%. And this is the spec of that sun. And the sun's total energy output is about 3.8 into 10 to the power of 20 megawatt, which is equal to 63 megawatt per meter squared of the sun's surface. This energy radiates outward in all direction, and the earth receives only a tiny fraction of the total radiation emitted, equal to 1.7 into 10 to the power of 14 kilowatt. However, even with this small fraction, it is estimated that 84 minutes of solar radiation falling on earth is equal to the world energy demand for 1 year, about 900 etajoule. When we look at the solar radiation, and it is so powerful, and we get enormous amount of energy, and we cannot tap the entire energy. Even when we tap even small fraction of that energy, and even when we able to store for just 84 minutes of solar radiation, whichever is falling on earth, and we can supply energy demand for the whole world for throughout the year. So that is so amazing. And when we look at what is happening in solar, that the sun is a hot sphere of gas whose internal temperature reaches over 20 million degrees Kelvin, 20 million degree Kelvin, due to nuclear fusion reactions at the sun's core, which convert hydrogen into helium. And so this is the chemical relation, and the hydrogen is converted into helium, and 0.277 mass units of matter are converted into energy. So the fusion reaction is taking place, and when we look at the core temperature of the sun, it is about 20 million degrees of Kelvin, which is so high, and we get only fraction towards the earth, and that too we are not able to store complete energy nowadays, and the solar technology is coming up in order to capture the solar radiation and make it useful. And every second 657 million tons of hydrogen are converted to 653 million tons of helium in our sun. The missing 4 million tons are converted to light and heat energy via Einstein's equation and radiated into the space. It is estimated that the remaining hydrogen in the sun's core is sufficient to maintain the sun at its present luminosity and size for another 4 into 10 to the power of 9 years. And this is about the solar fusion. And when we look at the solar spectrum, and electromagnetic waves or photons are characterized either by their frequency f or their wavelength lambda. The wavelength of solar radiation is given in micrometers, that is 1 micrometer, that is equal to 1 into 10 to the power of minus 6 meters, or nanometer, that is 1 nanometer, that is equal to 1 into 10 to the power of minus 9 meters. A photon can also be described in terms of energy that it carries. And distribution of solar spectrum in terms of wavelength and amount of energy carried, and from the solar radiation we have UV, that is ultraviolet radiation, visible radiation, infrared radiation, and other radiation. And this is the range of wavelengths, that is in micrometers, that is 0.15 to 0.38. The energy carried capacity is about 7.6%, and the visible radiation, the range of wavelength, it is 0.38 to 0.72, and energy carried capacity is about 48.4%. Infrared radiation, it is 0.72 to 4.0, that is the wavelength, and in micrometers, and the energy carried is about 43%. Other radiation, it is whatever it is greater than 4.0, then the energy carried capacity is just 1. And this is about the solar spectrum. It is a combination of UV radiation and visible radiation and infrared radiation and other radiation. And now, so we are going to see about the extraterrestrial radiation. So we have seen the specification of the sun, and so what are the radiation in the sun. So now, so we are going to concentrate on extraterrestrial radiation. So the amount of solar radiation received by a planet depends on its distance from the sun, and the earth is about 1.5 into 10 to the power of 11 meters away from the sun. The extraterrestrial radiation refers to the amount of radiation falling on earth outside its temperature. So extraterrestrial radiation, which is above the atmosphere, where there is completely vacuum, and the extraterrestrial solar radiation received by the earth is essentially constant throughout the year. So above the atmosphere, and it is fully a vacuum, that is, that region is called extraterrestrial radiation, and there the solar radiation is constant towards the year. That is why it is called solar constant. The extraterrestrial solar radiation is often given in terms of solar constant, which is defined as average radiation intensity received per unit area perpendicular to Earth's surface at mean sun Earth distance. The solar constant is taken as 1367 watt per meter square. It will never change, and above the atmosphere, and we have the region of extraterrestrial radiation, where the solar radiation is constant, and everywhere in the globe, that is 1367 watt per meter square. It cannot exceed beyond this. And radiation on the Earth's surface, The scattered radiation due to gaseous molecules and other particles in the atmosphere is called diffused radiation. And so, above the atmosphere, and so this is the earth, and this is imaginary line, that is atmospheric level, and above that, that is called extraterrestrial radiation. And this is this area from the earth to the atmosphere level, that is called terrestrial radiation. And in the extraterrestrial radiation, since it is above the atmosphere and it is full of vacuum, and here the solar constant is same throughout the year in the entire globe. But when it comes to the terrestrial region, that is just above the just below the atmosphere and above the earth, and there will be lot of gaseous molecules and other particles and dust, etc., and it reduces the effect of the radiation. The radiation gets diffused over here, that is why it is called diffused radiation. When radiation does not go through either absorption interaction or scattering interaction and reaches the earth surface directly, and it is known as direct radiation. And partially some radiation will not get affected by any interaction, or it will not be scattered, and partially that radiation will come directly to the earth, that is called direct radiation or beam radiation, and partially it gets disturbed and it gets scattered and it gets interacted with the gaseous molecules, then and it will become a diffused radiation. So, on the earth, and the what radiation we get is, that is direct radiation and the diffused radiation, both we are receiving on this earth, and the total is called global radiation. And and the total radiation is sum of direct radiation and diffused radiation, it is called global radiation. And and here, as I said, this is extraterrestrial region and this is terrestrial region, and this is the earth, and partially the radiation comes directly and partially it gets scattered, and when we add direct radiation and diffused radiation, then it is called global radiation. And these are some of the measurements and radiation measuring instruments, and what we see here, it is a pyroliometer. This is an instrument using a collimated detector for measuring solar radiation from the sun, that is called beam radiation. So, the pyroliometer, which is the instrument to measure direct radiation or beam radiation. So, this is the another instrument called pyranometer, and it is used for measuring the total radiation, that is beam radiation or direct radiation plus diffused radiation. It can be used to measure diffuse radiation only by using a shade ring or disc which shades the beam radiation. So, and we can cover the beam radiation with the disc, and then we can measure the diffused radiation using the pyranometer. Of course, the pyranometer is helpful to measure the total radiation, beam and diffused radiation. Okay. So, and so far we have seen about the solar system, that is the sun's effect and sun's dimensions, and the diameter of the sun, and how much energy is being released from the sun, and how much the earth is receiving, and what kind of radiation it is receiving, and what is happening in the extraterrestrial region and the terrestrial region, and what kind of radiation we receive, and in the radiation what are the radiations and wavelengths and the energy carrying capacity, everything we have discussed so far. And now, and so the main application of solar energy is solar water heating system, and this is what we are going to see, and this is one of the applications of solar energy. And from solar energy and from heat energy, and we get solar thermal systems, and from heat energy, and we can operate various solar thermal technologies, and from radiation, and through the semiconductor device, that is solar photovoltaic device, we can generate electricity. And now we are going to look at that, and from the sun, when the radiation reaches the earth, and when it strikes the earth, and we get the heat out of it, and from the sun's heat, and we have a lot of solar thermal energy technologies, and one of the technologies is solar water heating system. Of course, it is very simple technology, and it is quite mature technology, and the water can be heated up through solar energy, and the solar water heaters intercept solar radiation and use it to heat the water. Solar thermal collectors can be categorized by the temperature at which they efficiently deliver the heat. And here in this schematic diagram, and we are seeing here the flat plate hot water system, and this is the storage tank, and here the cold water, it is coming in from the tank through the solar flat plate collector, and this is the tank, and which is insulated properly, and at the bottom the pipeline is taken to take the cold water into the flat plate collector. And this is the cut section of the flat plate collector, and so this is the glass cover, and it is covered fully, and so here inside we have the water channel. Water channel, it is circular in size, and at the bottom this is the absorber coating. So, absorber coating is it is a black coating, so that the heat conductivity can be increased here, and this is about insulation, and both the sides, all directions have to be insulated properly, and there should not be any waste of heat energy. And here the sun is penetrating, the solar energy is penetrating above the glass cover, and it is coming inside, and the water is flowing through the water channel, and the water gets heated up, and it is going up, and it reaches the tank. You may be wondering how the water is going from the bottom to the top without any pump. Here we have just, this is thermosiphon effect, without any pump, and the water is traveling from bottom to the top. You may be wondering how it is possible, and when the water is heated up, and that when the temperature of water increases, the density decreases, right, and because of the density difference, and the water is flowing from the bottom to the top, and when the cold water comes in, it is higher in density. When it is heated up, and the density decreases, so the cold water will push the hot water into the tank, and then the cycle repeats, and the water could be heated up to 70 to 80 degree Celsius. This is a very simple flat plate hot water system, and which is conventionally it is used all over the India, particularly some of the states. For example, in Karnataka, this has become mandatory, and before they get approval of the housing, and they have to show, and they are going to install the water heating system, then only the approval will be given. And almost in all the houses they install the solar water heating system, and all over the world, and particularly in European countries and Israel particularly, and they install solar water heating system for the domestic purpose as well as in industrial purposes. And of course, it is also playing major role in hotel industries. And of course, this is very basic technology, very effective technology. The efficiency will be in the order of 40 to 50% and cheaper, and it is cost effective also. We can save and enormous amount of fossil fuels when we go for say water heating through solar energy. And this technology can be further updated. Lot of research is going on, and and hundreds of papers are published in solar water heating system. And for example, you can increase the efficiency of the system by changing by increasing the surface area of the water channel. That now it is circular, maybe you can increase the surface area like a hexagon or pentagon or any other shape, truncated shape, so that the surface area can be increased, and so the performance of solar water heating system also can be increased. That is one aspect. Another one, and people use and like nanoparticles, and so by which again the heat conductivity can be improved, and people do research how to bring down the cost here. Maybe they go for and cheaper cost of the materials, and they try various insulation material, and they just optimize the system, and they try to bring down the cost, and they try to enhance the present efficiency, and lot of research is going on in the solar water heating system. And this is about a slightly advanced water heating system here, and here that is mainly for hotel industries or and industrial applications where thousands of liter water is required. And here this is about the solar collector. It may be flat plate, or it may be a parabolic trough collector or Fresnel collector, whatever collector you can have here, that is the solar collectors. And here this is the water tank, and here the hot water is coming and gets stored here, and this is the cold water supply here, and the hot water is taken from above and for the purposes, and then here we have the heat exchanger, and the heat exchanger, and here I mean the water is coming from the tank, and it is pumped. This is full circulation, and the water is passing through the heat exchanger, and it absorbs heat from the heat exchanger, and the cold water becomes hot water, and it comes to the tank, and then it is taken for the various purposes. And this is the circuit. This is the cold water comes in and hot water comes out, and this is the heat exchanger. And in the heat exchanger, here we have the distilled water, and the distilled water is taken through the pump, and it gets heated up through the solar collector when it is passing inside, and then it comes back. And here we use distilled water, it gets heated up quickly. Not only that, and the solar collector tubes will not be corroded over here. That is why we have a distilled water circuit here, and this is the heat exchanger, and the heat is transferred from the distilled water to the normal water, and then it gets heated up. And apart from it, and if the industry needs higher temperature, and then we can use terminal oil or some other working fluid, and which can take more amount of energy from the collector, and from which that heat can be transferred to the water, and the hot water can be stored in this tank, and it will be useful for the industrial applications, and this is for higher capacity. And these are the various components of solar water heaters, and in general it consists of three main components, and the solar collector, which converts solar radiation into useful heat, and heat exchanger and pump and controller module, which transfers the heat from the solar collectors into the potable water, and storage tank to store the solar heated water. And this is the heat exchanger, and this is the pump. This is because it is forced circulation, and these are the storage tanks, and this may be in industries, and that is in industrial water heating system. And these are the various collectors, and for example, and to have a low temperature, maybe up to 32 degrees Celsius, unglazed glazed absorbers can be utilized, and if you want to have a medium temperature up to 70 degrees Celsius, then glazed flat plate collectors can be used, and integrated collector systems, that is thermosiphon and antifreeze and drain back system can be utilized. And for the high temperature applications, then we can look for evacuated tube. You can go up to 175 degrees Celsius, and then you can also go for parabolic trough collector, and through which you can go up to 300 degrees Celsius. These are the various solar collectors and glazed absorbers for low temperature applications, and flat plate collectors for medium temperature applications. And for high temperature applications, you can go for evacuated tube and then parabolic trough. And here you are look at the pictures of various solar collector types, and this is unglazed collector, and this is about low cost plastic flat plate collector, glazed insulated flat plate collector, and this is parabolic trough collector, and here you see evacuated tube collector. So, there will be no air inside, the heat transfer will be very effective. This is about integral collector storage system. And of course, and here you get low temperature and medium temperatures, and when you go for parabolic trough collector, and this is the absorber in the parabolic trough collector, and this is the collector, the sun rays will strike the collector and it gets reflected towards the absorber, and the absorber area is very small, but the collector area is big. That ratio is concentration ratio, the ratio between the collector area and absorber area, that is the concentration ratio. This is when the concentration ratio increases, and you can get more temperature output, and normally the terminal will be flowing in the receiver, and then through which heat can be transferred to the water, and the evacuated tube again, and since the air medium is not there, the heat transfer will be effective. So, and according to the applications, we can go for various types of collectors available, and people even nowadays they invent a lot of new collectors for various applications like Fresnel collectors and etc. So, and so far in this particular lecture, and we have seen so far about the sun's specification, and how what are the dimensions of the sun, and how much energy we can derive from the sun, and how much energy is coming to the earth, and what are the radiations available, and then and about the what is happening in the extraterrestrial region and terrestrial region, and what kind of radiation we receive to this earth, like global radiation, that is direct radiation, and diffused radiation. And then and with this heat energy, and there are lot of applications are possible from the solar sun energy's heat, and one of the applications we have seen so far, that is about solar water heating system, and for the domestic applications as well as for the industrial applications. And we have seen lot of solar collectors, and still the performance could be increased, improved by going for some advanced collectors, and increasing the surface area of the absorber, and even using nanofluids. And with this I stop the lecture. Thank you so much.